Welcome back. Functional Analysis FAV 028 by Prof.Dr.A.G. Srinivasan. In this series of lectures, you will learn inner product space, Hilbert space, properties, orthogonal complements and direct sums, orthonormal sets and sequences, representation of functionals on Hilbert space, Hilbert adjoint operator, self-adjoint unitary and normal operators. This is a very simple module starting from inner product space to normal operators. Before we start doing the inner product space, just recall the definition of a mapping. What is X? X is a non-empty set. X is a non-empty set. X cross X is the Cartesian product of X with itself. An inner product denoted by this symbol is a mapping from X cross X to K, where K is either set of all real numbers or set of all complex numbers. So basically, inner product, if I write inner product X comma Y, it means that X and Y belongs to X as an ordered pair, and the inner product X comma Y belongs to K, where K is either R or C. R is set of all real numbers, C is set of all complex numbers. So what is important here? Though X is a non-empty set, it can be any set, the inner product X comma Y is always a real number or a complex number based on the K value. So KR means the inner product is R. K is complex means inner product is complex. That's the first point. Now, I'm just saying the word inner product, but inner product is not a term, it's a set of axioms. So if this is a symbol for the inner product, for X cross X to K, where K is R or C, then it satisfies the following condition if you want to claim that this is an inner product. Number one, inner product of X plus Y comma Z is inner product XZ plus inner product YZ. So if you take inner product X plus Y comma Z, it's inner product XZ plus inner product YZ. One more important point, if you have the inner product XY, and because X and Y are belongs to X, this X is called the first component of the inner product, and this Y is called the second component of the inner product. So the first axiom is the first component sum is sum of the first components. Inner product X plus Y comma Z is inner product XZ plus inner product YZ. The second property is that inner product alpha X comma Y is equal to alpha times XY, where alpha belongs to K, which is either R or C. Now remember, alpha is the first component. When alpha is removed from the first component, it becomes only alpha. But if alpha is in second component, it is not going to be alpha, as we see little later how it changes. The third important condition of inner product is that inner product XY must be same as inner product YX bar, where bar represents the conjugate. However, we already said the inner product is a real number, which is either R or C. If inner product is a real number, then there is no bar, the bar xy bar is same as yx bar is same as xy. There is no bar, no conjugate of the real number. However, if x comma y is a complex number, an inner product is a complex number, then the conjugate of that is going to be equal to x comma y. So x comma y is a conjugate of y comma x bar. Of course, if they are real numbers, x comma y is same as y comma x. And the fourth condition for the inner product is that inner product xx must be greater or equal to 0. So inner product xx must be greater or equal to 0. And the last condition, inner product xx will be 0 if and only if x is equal to 0. So let's recall the definition of an inner product. So an inner product, this is a mapping from x cross x to k, where k is equal to r or c, such that for every xy belongs to x, the inner product xy belongs to k, satisfying the following properties: x plus y comma z is equal to xz comma yz, alpha x comma y is alpha times xy for every alpha belongs to k, xy is equal to yx bar, x is greater than or equal to 0, and xx is equal to 0 if and only if x is equal to 0. Now, an inner product space, also called as IPS or a pre-Hilbert space, is a vector space with an inner product defined on that. So, besides the inner product, it is also a vector space. So, this X becomes a vector space with an associated inner product. So, an inner product space or IPS or a pre-Hilbert space is an inner product space associated with an inner product. Now the third point is very interesting. It says that if x comma y, okay, I'll put this way, if x is an inner product space, which we denote by this symbol, it means that x is a vector space, and this inner product is an inner product. Now what we talk about satisfying these 5 axioms of inner product. So if x comma, the conclusion is if x comma this is an inner product space, then I define norm x is equal to positive square root of the inner product xx, where x belongs to x. So take x belongs to x, take the inner product xx, take the positive square root of that, that is called the norm of x. Of course, I am calling norm. We are going to see little later that this norm in fact is a norm of x. We are going to show later that this is a norm in fact. Note that we already saw in the definition of inner product space definition, the inner product xx is always a real number. Okay, it's always a real number. So this is well defined, and norm, you know, is always a real number. So it's a positive square root of xx. Therefore, norm x is always also positive. We will see little later. This norm is in fact a norm. It satisfies all the properties of the norm, which we'll do after a few discussions. So norm x is defined as inner product xx with a positive square root. And you can show, we are going to show a little later, this is in fact a norm. Therefore, every inner product space becomes a normed space. Every inner product space becomes a normed space. We are going to say a little later about that. Now, if x is a normed linear space, if x is a inner product space with a norm, we'll define d of xy as norm x minus y, which is positive square root of inner product x minus y comma x minus y. So take the inner product of x minus y and x minus y, which is a real number, take a positive square root of that, that is defined as norm x minus y. And this is called d of xy. It is easy to show that this is x comma d is in fact a metric space. But we will not show this because in the previous videos we have showed from the norm how to construct a metric space like this, and we proved in those videos that d of xy is in fact a metric. So every inner product space, there is a normed space. Every normed space associates a metric space. But a metric space need not be a normed space. A normed space need not be an inner product space. So just recall one more time what we discussed about the inner product space. So definition of inner product is that it's a mapping from x cross x to k, where k is R or C, satisfying the axiom x plus y comma z is x z plus y z. Alpha x comma y is alpha xy for every alpha belongs to k. Xy is equal to yx bar. Of course, inner product xy is inner product yx bar, where bar represents the conjugate. If k is C, if k is R, there is no conjugate required. Inner product xx is greater than or equal to 0. Inner product xx is equal to 0 if and only if x is equal to 0. And what is the inner product space or a pre-Hilbert space? It's a vector space which has an inner product defined on that. And we denote an inner product space or IPS by x of this symbol. Now, if x this is an inner product space, then the inner product defines a norm. We are going to show this is a norm by the formula norm x is equal to positive square root of xx. This is positive square root of inner product xx, and the metric d of xy is norm x minus y, which is again positive square root of x minus y comma x minus y. Now we are going to discuss some more properties of inner product space. Now, the following properties in inner product space is shown below. It's very interesting property and simple properties. What we have discussed is inner product of the first component x plus y comma ez is xz plus yz. So in that context, it is easy to show if alpha and beta are two scalars, any two scalars belongs to R or C, the inner product alpha x plus beta y comma z is equal to alpha xz plus beta yz. Inner product x alpha y is alpha bar inner product xy. The third property is that inner product x comma alpha y plus beta z is alpha bar inner product xy plus beta bar yz. The proof is very simple. Let us do it without much discussions because it is a very simple proof. We will prove first one, which is inner product alpha x plus beta y comma z is alpha x plus z. Now we are going to show that this is going to be this. Now take the first component, which is alpha x, and first component beta y. So it's going to be alpha x z and beta y z. So by using the definition, the first component, no, x z and y z. So first component is alpha x, and second component is alpha x comma z, and beta y is again first component comma z. I'm just having this, right? Now alpha can be taken by the second axiom of the inner product, alpha x comma y. If alpha is the first component, it is alpha times xy. So using that, you will get alpha times xz plus beta times yz. This shows that inner product alpha x plus beta y comma z is alpha times xz plus beta times yz. Now to prove second one, x comma alpha y is alpha bar xy. We want to show that if alpha is the second component, alpha will come out as alpha bar into xy. That's very easy because x comma alpha y by the second axiom is alpha y comma x the whole bar. It's a complex number if it's a complex number. So alpha can be taken out because alpha is now in the first component. So it's alpha bar because bar is always there in that. So alpha bar yx bar. But yx bar is again xy by definition of inner product. So x comma alpha y is alpha bar into x comma y. Now to prove 3, which is x comma alpha y plus beta z is equal to alpha bar x is xy plus beta bar xz, it's a combination of first two properties. How to do it? X comma alpha y plus beta z is equal to alpha plus beta z comma x the whole bar. So I can divide into two parts of the first component like. So alpha y comma x bar, beta z comma x bar. So alpha bar can be taken out because alpha is not the first component now. Alpha bar yx bar plus beta bar is x bar. So this is alpha bar. Again we invert yx bar as xy by property of the inner product plus beta bar xz. So we proved that inner product x comma alpha plus beta z is equal to alpha bar xy plus beta bar xz. Now the next result we are going to show is this norm is in fact a norm. Okay, what is the norm definition? The norm definition is uh, norm x is equal to positive square root of inner product xx. So before I do that, let's take what is an inner product notion. So the point is that inner product xx is always greater or equal to 0. That means this must be a real number. Even if the inner product xy is a complex number, even if this is a complex number, inner product xx is going to be a real number. That's the first point. So if you use definition of this notation I called as norm x is positive square root of xx. The observation is that norm x is also a real number. Of course, I have to show norm x is in fact a real number, but this definition of this guarantees it's a real number because it is a positive square root of a real number. It can't be a complex number, right? However, what is interesting is if norm x is positive square root of inner product xx, what is interesting is that norm x square equals xx inner product. So if you square on both sides being a real number, norm x square is inner product xx, which is always greater or equal to 0. So norm x is greater or equal to 0, it's a real number, of course a positive real number, and even norm x square is also a positive real number. That's the first point before we do it. Now we are going to show that in fact this definition norm x is equal to positive square root of xx is certainly is a norm. So we are going to show this is a norm definition. What are the properties of the norm? Number one, norm x is greater or equal to 0. Number two, norm x is equal to 0 if and only if x is equal to 0. Norm alpha x is modulus alpha into norm x. And of course the famous triangle inequality norm x plus y less than or equal to norm x plus norm y. So to show this is a norm, I need to verify these four conditions. Now the first condition is very obvious because just now we discussed that norm x is always greater or equal to 0. And norm x is equal to 0 implies inner product it means that norm x is equal to 0 implies that inner product xx is a product square root of that, it's 0, square on both sides, inner product xx is 0. But by very definition, inner product xx is 0 if and only if x is equal to 0. Just recall the definition of inner product xx is equal to 0 if and only if x is equal to 0. So what is the conclusion we make? We make that inner product x is equal to 0 if and only if x is equal to 0. So you can see that this axiom is verified. This axiom is verified. Now I verify this axiom. What is that? Norm of alpha x is modulus into norm x. For this, let me start with what is a norm of alpha x. This is by definition positive square root of inner product alpha x comma alpha x. Now alpha can be a complex number as well. Need not be a real number. Alpha can be a complex number or it can be even a real number. That's not important. It can be anything. Let's see what happened to this. Now first thing what we do is we square on both sides. So this implies norm alpha x the whole square is equal to inner product alpha x comma alpha x, where alpha could be a complex number or even a real number. That is not important. But what is interesting is that view the alpha in the first component. So I can remove this alpha here, inner product x, because I removed from the first component. When I remove second component, I would get alpha becomes alpha bar, which is again x. So this is alpha bar x. And if alpha is a complex number, alpha into alpha bar is modulus alpha square. And if alpha is a real number, it's going to be alpha square. So in any case, it's going to be same. Okay. So this is going to be inner product xx. But you know, by definition, this is going to be inner product. Therefore, inner product, sorry, the norm alpha x square is modulus alpha square into inner product xx. So this certainly means that norm alpha x square is equal to modulus alpha square. And you know what is inner product x square? This is norm x square. Now take a positive square root of this, you would get norm alpha x is equal to modulus alpha into norm x. So it's easy to verify that the third axiom, which is norm alpha x is equal to, is equal to modulus alpha and norm x, is verified. Now we need to prove that norm x plus y is less than or equal to norm x plus norm y. If we prove this for this inner product norm, then it is easy to show that it is a norm. So let's take the version here. So we are just proving it again. So we just see that norm x greater than or equal to 0, norm x equal to 0 if and only if x is equal to 0 using 4 and 5 of 1. So what is 4 and 5 of 1? This is 1. So this is 4 and 5. I'm using those two to prove the first two axioms. Okay. Now proving norm alpha x equal to modulus alpha x into norm x is easy. You can see the proof automatically. We prove it. Now we are going to show the triangle inequality norm x plus y less than or equal to norm x plus norm y. But for this, we require the following lemma. The lemma is as follows. We need first a Schwarz inequality to prove this. Then we will use this Schwarz inequality to prove triangle inequality. What is Schwarz inequality? It says modulus of inner product xy is less than or equal to norm x into norm y, and equality holds if and only if either y is equal to 0 or x and y are linearly dependent. So modulus of inner product xy is less than or equal to norm x into norm y. Then using this, we will prove norm x plus y is less than or equal to norm x plus norm y, which is a triangle inequality. And again, the equality holds if and only y is equal to 0 or x is equal to cy. So to prove this, we'll do like this. Now, the first observation is as follows. Now, first of all, we know when x and y belongs to x, first you know that this inner product xy is either a real number or a complex number. So when you take modulus xy, the first point is that this is a real number always, because modulus of a complex number is also a real number. So if z is a plus ib as a complex number, modulus z is positive square root of a square plus b square. So this modulus of the inner product xy is always a real number. That's the first point. Therefore, this is meaningful to define modulus of the inner product xy is less than or equal to inner product, the norm product of norm x into norm y. Because this is a real number less than or equal to norm x and norm y. Because you know that two complex numbers you cannot compare. You can't say one complex number is more than the other complex number, because complex numbers are not comparable. Okay, that's a very interesting part of complex numbers. Whereas in real numbers, you observe that inner product xy is less than or equal to norm x and norm y is certainly meaningful. Now, before we go to this, let's take the inner product xy first. We are going to show that inner product xy is actually equal to norm x into norm y if y is equal to 0. We are going to show first inner product xy. Of course, modulus also can be taken. Modulus inner product xy is equal to norm x into norm y. Now, this first case we are going to show. Now, if it's very obvious, if y is equal to 0, we already proved that norm y is equal to 0. This implies norm x into norm y is equal to 0, because if y is equal to 0, norm y is 0. So norm x into norm y is norm x into 0, which is 0. So I'll call this equation number 1. Okay, I'll write one more time this just for reference. Norm x into norm y is 0 if y is equal to 0. Now, we want to show something else. So we are going to show like this. We are going to show that inner product xy is 0 when y is equal to 0. Or equivalently, we need to show that inner product x0 is 0. We are going to show that inner product x0 is 0. Now, we assume for the argument's sake that inner product x0 is not equal to 0. Let's see what happened to this. Inner product x0 is not equal to 0. We wish to show inner product x0 is equal to 0, which I will call it as 2. We want to show 2, but I assume inner product x0 is not equal to 0. Now, just we take inner product x0. This x0 can be replaced as inner product x comma alpha times 0 for some alpha belongs to k, where k is r or c. You know, in a vector space, alpha 0 is always 0. Alpha is a scalar, 0 is a vector, so alpha 0 is again a vector. But by definition of inner product, when I take alpha out from the second component, this becomes alpha bar x0. So what we proved so far is that inner product x0 is equal to alpha bar inner product x0. But because x0 is not equal to 0 as assumption we made, we can cancel the x0 and x0 because it's not equal to 0, it's a real number. This should imply alpha bar is equal to 1. And if alpha bar is 1, if alpha is the conjugate complex number, then suddenly alpha becomes 1 as well. Because alpha bar is 1, which is not having any complex component, so alpha bar is equal to alpha is equal to 1. That's not important, but we make an observation, alpha bar equal to 1. Now, so if x bar is not equal to 0, and if you take this equation, we have alpha is equal to 1. This itself is wrong because for any alpha, you need not say alpha bar is always 1. But that's okay, that's fine. It's not false because when alpha is 1, you get x is equal to 0, x0 as such. That's not a big issue at all. But what we're going to do now is something else. Okay, now let's take inner products x comma alpha y plus beta z. Just take inner product x comma alpha y plus beta z for some alpha and beta. The alpha and beta is important for me. I just take 2 alpha beta as I like. But this is by definition alpha bar xy, because alpha in second component, plus beta bar xz. You know this by the property we just now proved. Now I'll assume again y is equal to 0. When y is equal to 0, what is left hand side? Left hand side is x into x comma. Y is 0, so alpha into 0 is again 0. It's a 0 vector. 0 vector plus beta z is again beta z because it's a vector space. So under addition it is a group. So beta z plus 0 is again 0. So this term will vanish. You simply have x comma beta z. On the right hand side, this is alpha bar, and y is 0 we have taken, so x comma 0 plus beta bar, it is xz, no change. It is xz, no change. But you know, from the lower discussion we have few minutes back we had, the inner product x beta, the beta is the second component, is same as beta bar inner product xz. Okay, x beta z is beta bar xz. So I can just take beta outside the second component. So this equation, left hand side becomes, you know, as you observe, it becomes beta bar xz, and the right hand side is alpha bar x0 plus beta bar xz. And by mathematical term, they are real numbers. I can cancel both sides because both are real numbers, including beta bar. I can cancel, so beta bar xz is cancelled. So what I have now is alpha bar x0 is equal to 0. And because we assume that alpha bar is equal to 1, we have constructed alpha bar equal to 1, it means that I can bring the alpha bar this side. So x0 is equal to 0 by alpha bar, which is again 0 because they are not equal to 0. So this means that x0 is 0. But we assume that x0 is not equal to 0. How it is possible? Therefore, x0 is automatically 0. If x0 is not equal to 0, I get a contradiction, x0 becomes 0. Okay, but therefore x0 is not equal to 0 as well. So what we proved at the matter of fact is no x comma y is equal to 0 if y is equal to 0. I will call equation number 3. So one says, you can just go to that one equation. One says norm x and norm y is equal to 0, y is equal to 0. 3 says 3 says xy is equal to 0, y is equal to 0. That means norm the inner product xy is 0 if y is equal to 0. Norm x into norm y is equal to 0 if y is equal to 0. So combine these two, you observe if y is equal to 0, inner product xy is equal to inner product x into inner product y. That's the first observation we observe it. So the equality holds. Of course, modulus can be taken because already it's 0 only. So modulus inner product xy is norm x into norm y. So if you take the cross inequality, norm x y is equal to norm x into norm y if y is equal to 0 as a matter of fact. Of course, we will prove this a little later. Now we are going to show this next. So you assume that y is not equal to 0. Let's take this equation here. So first we show that inner product x is equal to 0, and if x0 is not equal to 0, then we have constructed alpha bar equal to 1, all that, then alpha equal to 1, etc. The next term alpha plus beta is taken. All these things I explained to you a few minutes back. You can use that property x beta is beta by x z, all that. So you get back this, again this is 0. So thus inner product 0 is equal to 0. Now I assume that this I'm going to prove by assuming that y is not equal to 0. So assume that y is not equal to 0, and I'm going to find out something else. Now to do this, let me take the explanation here. Okay, so now let y not equal to 0, we would like to show modulus inner product xy in this case is less than or equal to norm x into norm y. Now choose an alpha belongs to K. This alpha need not be this alpha. Okay, that's already over. I'm taking some scalar alpha in this. Then by simple mathematics, you can see that norm x minus alpha y is greater than or equal to 0 for every x comma y. What is the reason? You know, norm is always non-negative. We know that. So norm x minus y alpha y is always greater than or equal to 0 for every alpha belongs to K. For some alpha, okay? This is for some alpha. This alpha can be anything as you like in K. Now this would imply, I just square it, this would imply norm x minus alpha y the whole square is also greater than or equal to 0. We already saw that in the previous discussions. And now 0 less than or equal to norm x minus alpha y whole square for, of course, any alpha. I decided for some alpha because it's true for any alpha. I will take some alpha as I like and then do this. But what is the definition of a norm in the concept of inner product? This is inner product x minus alpha y, comma inner product x minus alpha y. So, of course, this is true for every alpha. Please remember, but at least it's true for some alpha, that is guaranteed. So I just take is equal to inner product x comma alpha y comma x minus alpha y. This we write very cleverly. That's the cleverness of cross inequality. What is the first part? Xx, inner product xx. Now second part is inner product alpha y comma x in the first component. So minus alpha inner product yx. Then I will take these two, maybe I'll take these two, which is x comma minus alpha y. So plus x comma minus alpha y as the inner product. And then these two, which is plus minus alpha y comma minus alpha y. We expand the inner product by using the properties and definition of inner product. Now let's take this first. This is equal to inner product xx. So I'm not disturbing this. This is over. Now what I will do is I will take this. Now this alpha is in second component. So I will have alpha pull out from this. Therefore it's become alpha bar with a minus sign. So minus alpha bar inner product xy. Okay. Alpha is in the second component. Minus of course is there. When you pull out, you get, maybe I'll just take it this minus. You will get minus alpha bar into xy. Okay. Next, so this is also over. Now this I am not disturbing for time being. I will write minus alpha yx. Now here I will do very carefully this step. I will write still plus because there is a minus. I will take it outside, so I get minus there. There is a minus. When I take it outside, I get minus there. So minus to minus is plus. That's the first point. Now alpha is taken from the first component. So minus is taken out. We don't require it. Alpha is the first component. It is alpha. This alpha is second component. I am taking outside. I get alpha bar. And this is going to be y comma y. Therefore, let me write again this part again one more time. So this means 0, 0 less than or equal to x minus alpha y the whole square, which is equal to, this is equal to, this is equal to. So what we have, what is this? What is this? This is norm x square. This is norm x square. And I will write this term first, minus alpha bar xy. I am not disturbing that even. Now what I will do is, I will take minus alpha common. I go very slowly. Minus alpha common. If I do that, the first term is yx. The inner product ys, of course. The first term is inner product yx. Now since I have taken minus alpha common, I get a minus sign here. Alpha is taken common already. So I get alpha bar inner product yi. So that's why I'm writing it. Minus alpha bar inner product yy. That's the interesting part. Okay. Now what I do is, since this is valid for every alpha, I will choose alpha bar. I will choose alpha such that alpha bar is equal to inner product yx by inner product yy. Now you know pretty well yx, inner product yx could be a real number or a complex number. Inner product yy is always a real number, cannot be 0 because we assumed y is not equal to 0. Therefore this is a complex number if the field is k, if the range is k, or it is a real number and alpha bar becomes alpha. So I choose alpha bar such that alpha bar is equal to inner product yx by inner product yy. Now if I do that, what is going to happen is, I will cross multiply alpha bar inner product yy minus equal to inner product yx, or inner product alpha bar inner product yy minus inner product yx is equal to 0, or inner product yx minus alpha bar inner product yy is equal to 0. So if you have chosen alpha bar in this way, you will get inner product yx minus alpha bar yy is equal to 0, which is this. You see that? yx inner product alpha bar yy is equal to 0. So yx minus inner product alpha yy is equal to 0. So if we choose alpha bar in this way, this component becomes 0, this component would become 0, and 0 and alpha is 0, so the whole term will vanish. So if we take alpha bar as inner product yx by inner product yy, the whole term will vanish. So what I have now is the following. Let me write that again. So 0 less than or equal to, I write only this term, 0 less than or equal to, I will write norm x square, I will write that first, norm x square minus, what is alpha bar? Alpha bar in this term is inner product yx by norm y, no, in this case, inner product yx by yy, and you have still left out with one more term xy, so this is xy, and these terms, all of them vanish, you don't have to do it. That's all, we have done it. Now this is nothing but 0 less than or equal to norm x square minus, this is nothing but, y is nothing but xy bar. By definition of the norm we have discussed, yx is nothing but xy bar into xy, that's the first part, divided by denominator is norm y square, because yy is norm y square. And what is this? Xy and xy is nothing but 0 less than or equal to norm x square minus modulus inner product xy square, because z bar in complex numbers, z bar is modulus z square by norm y square. So if you rewrite this, if you bring all this term one side and so on, you will get, thus you will get inner product xy square is less than or equal to norm x square into norm y square. So you can just get this and bring this term here and then bring all this and take the square root, a positive square root. We have modulus inner product xy is less than or equal to in norm x into norm y. So we proved the Schwarz inequality. Now the equality can happen only if this becomes equal to 0. And this equal to 0 should imply that x minus alpha y is equal to 0. So to get the equality, if y is not equal to 0, to get the equality you should have x minus alpha y norm must be equal to 0. Only when it is equal to 0, this becomes 0, equality happens. If y is not equal to 0, of course, if y is not equal to 0. And by definition of a norm, norm x minus alpha y is equal to 0 if and only if x minus alpha y is 0, which in turn means this implies x is equal to alpha y. This in turn implies x and y are linearly dependent. So linearly dependent means you can express one in terms of the other, where of course alpha is not equal to 0. Because if alpha is equal to 0, this is meaningful, because when alpha is 0, x becomes 0, nothing to worry. So if alpha is not equal to 0, you have the inner product, you have x and y are linearly independent. So what we proved now is this. So we proved all this. So we started with this equation and we written this way, and then xx, alpha yx minus alpha bar xy, all that stuff, alpha bar yy, and then these inequalities. Choose alpha bar because this inequation is valid for any scalar. For any scalar is valid. So I fix this scalar. If you choose this scalar, this becomes 0. I get my equation automatically. And obviously we can see that they are linearly independent because they are equal to 0. Now finally we are going to show a triangle inequality using this. It's very easy to prove it. We are going to show that norm x plus y the whole square. This definition is inner product x plus y comma x plus y. I can use definition of inner product xx, xy, yx and yy. You can see that. And the xx is norm x square. You can see this norm y square. This is norm x square. This is norm y square. And yx, is basically x. Okay, if you want to write that somewhere so that we don't miss it. So let me do the triangle inequality. We would like to show that norm x plus y is less than or equal to norm x plus norm y. Now to do this, let me start with x plus y the whole square This is inner product x plus y comma x plus y. This is equal to inner product xx plus inner product yx. So you can take these two and then these two plus inner product xy yy. So inner product xy plus inner product yy. Okay. Now this is becomes, basically left hand side, inner product x plus y the whole square is equal to, these are all equal to, first term is, this is norm x square. So this is going to be norm x square plus this is going to be norm y square. So I'll write that next. Then we have the first term. I'll write xy term, inner product xy term plus inner product yx. Inner product yx is going to be xy bar. Inner product xy is xy bar. Okay. So this is equal to norm x square plus norm y square. So x plus x bar or z plus z bar in complex numbers, z plus z bar is 2 times modulus x y inner product thus. Z plus z bar is 2 times real part of x, etc. You know that. So modulus x. But you know what is this is equal to? This is equal to, this is less than or equal to, sorry, norm x square plus norm y square plus 2 times norm x into norm y, because by Schwarz inequality, modulus inner product xy, you can check it here, inner product modulus xy is less than or equal to norm x into norm y. So this becomes inequality. But this is nothing but this equal to, this actually equal to norm x plus norm y the whole square. Norm x plus norm y the whole square. So left hand side is norm x plus y the whole square less than or equal to, because the less than or equal to here is norm x plus norm y the whole square. So if you take the square root of positive square root, we have norm x plus y is less than or equal to norm x plus norm y, and equality holds only if this will be equal to this, this will be equal to this. Okay, and that is going to happen only if y is equal to 0 or x and y are linearly independent or x is equal to alpha y. So that's what the proof says. So we are using this and we proved that it is a triangle inequality. So it's easy to prove the same argument, it's easy to prove the triangle inequality. And this completes this video. We will see in the next video more about this pre-Hilbert space, inner product space, and some of the very interesting properties. This is Professor Dr. A.G. Srinivasan. Thank you.